students, this is Mr. Bornheimer, and we're going to go ahead and start kind of this notes packet on circular motion. A couple of things before we begin. First of all, make sure that you're staying on top of those reading quizzes. The reading quizzes need to all be taken by December the 13th, so I really want you to focus on getting those taken. A couple of other things to keep in mind, that there's the new question forum online, and you can check that out on bclassroom.com. There's a post on the front page, but there's also a link under the student tab, and also a link for the question forum / homework questions page on the quick menu, which is on the right hand side of the B Classroom page. So please take a look at those two things and make sure that you are exploring them, especially with finals coming up and whatnot. So we really are mostly done talking about circular motion. And one of the things that I really want to focus on today is just kind of a little bit of a review of what we've been talking about, and then go ahead and taking this yet one step further and adding two equations and how we might use those equations. So we're going to go ahead and just kind of recap here. First of all, scenario, you have a yo-yo and it's attached to a string fixed at one end. Fixed means that right here in the very center of this circle, that it's fixed. And it's traveling in uniform circular motion about its center. Okay, uniform circular motion implying that the yo-yo is traveling at a constant speed. Okay, so we need to draw, if we want to draw a vector for the yo-yo's velocity, we're going to go ahead and we would draw that velocity such that if the string were to break, in what direction would the yo-yo go? And in that particular case, the velocity would be kind of like out here. Okay, so this is kind of like our velocity. Okay, now the other question we need to answer here is it accelerating? And from our discussion in class, we know that yes, indeed it is accelerating. The reason we can say it's accelerating is even though it might be moving with a constant speed in a circle, it's changing direction at every point in time. So when it's here, it's not going the same direction as it was. When it's here, it's not going the same direction that it was. When it's here, it's not going the same direction that it was. When it's here, it's not going the same direction that it was. Okay, and so on and so forth. So in order to kind of draw that from our notes, we know that acceleration is actually acting towards the center of motion. Okay, so acceleration is kind of acting in this direction. All right. Now, if the object, the mass, is accelerating, there must be a force acting on it in some way, shape, or form. So, yes, there is indeed a force acting on the yo-yo. And that force is also center-seeking. Okay. So we have the velocity, the acceleration, and the force. Now, if we go ahead and move down the page here, it says if the string holding the yo-yo in its path were to break at the point indicated in the diagram, how would the yo-yo's path change? Well, currently it's in a circular path, and it's fixed in that circular path because of the string, which is the radius, holding it there. But if that string were to break, the yo-yo would kind of travel off in a straight line at the point of breakage. And in this particular problem, if we were to assume it was to break at the exact point here in this diagram, it would continue off in this direction until either it came to a stop or something acted against it to slow it down or something like that. Okay, so there we go. That's really the front page. So just a very simple introduction to circular motion. Okay. So at this time, why don't you have your packets, why don't you go ahead and turn to the second page, okay? Imagine that you're a car traveling in a roundabout. Some of you have traveled in roundabouts before. Some of you have not, okay? And a couple of things we want to first recognize is that this roundabout has a radius here, okay? And the car is traveling in this circular path like so. Now, one of the things that we talked about in class was that it was important to kind of look at the different variables that differentiate circular motion from linear motion. Linear motion being what we've been looking at, circular motion being kind of this new thing. And those variables were time, okay, distance, velocity in a certain way, we'll talk about that in just a minute, acceleration, okay, force, and mass, and we kind of introduced these variables. And we talked about the time that it takes for this car to go around one complete revolution. Okay, so we're going to just kind of write in here that the time it takes for one complete, oh, kind of messed up there. Kind of want to click off that here. And we'll just go ahead and fix this. For one complete revolution. Okay, this time is actually also known as capital T, and it represents the period of motion. And this will actually become more important for us when we're talking about waves and sound later on. Okay, so distance here. Distance, okay, is basically how far the object's going to travel. And we know that it's traveling, or we're assuming it's traveling in a perfect circle. So really we're saying we're starting at this point, going in this direction, and we're going all the way around the circle until we get to that point again. Well, that's one full rotation or revolution, and we can describe the path of that car's motion by looking at some of our basic geometry functions, in this case circumference. So the equation we're looking for here is 2 pi r. Okay, that's the equation for circumference. And if you think back to velocity, you know that, or at least the idea of, and I guess for a moment, let's not even call it velocity. Okay, let's call it just speed. All right, how fast an object's traveling. It would be distance over time. So we can literally say that this car is traveling with a speed of 2 pi r, so the distance it travels, over the time, or in this case, the period. One full revolution. Capital T and lowercase t for circular motion are going to be very, very similar. Okay, and I know that when we talked about this in class, I introduced it as lowercase t. I'm kind of differentiating now, just to kind of bring it up, but you won't see much of a differentiation in your homework nor on your tests, or I should say the final exam. So, but just be aware of the fact that we call time in these kind of problems where you have something kind of coming back to where it started, a period. One period of motion is the time it takes for something to complete one revolution. Okay, so here we go. Now, that speed, okay, is how fast it's going, but because the car is changing direction, it is a type of velocity, and because the velocity acts tangent to the circle, we call this here the tangential velocity. So the tangential velocity, and I'll even just note it as kind of like v sub capital T, is going to be equal to 2 pi r and over capital T. And we're actually going to come back and look at this again in just a few moments. Okay, so we have distance here is kind of like the circumference. We have the tangential velocity, which is equal to 2 pi r over capital T. And now we want to look at acceleration. And acceleration is a slightly more complicated to explain. There's actually a really good breakdown in your reading, in your textbook, on where the formula for centripetal acceleration comes from. And if you are kind of curious about that, then you can check that out. But centripetal acceleration is actually v squared over r. Now, one of the things we didn't look at in this class, or on Monday, was we didn't look at what this might look like if we maybe didn't know velocity, but we knew the period. Okay, so what we can do is we can substitute in this equation for the velocity tangential and come up with yet another form of the equation for acceleration. Now, because the acceleration is center seeking, it's going to have a lowercase c here, meaning centripetal. Okay, and we see that word show up over here on the right-hand side as so. So centripetal acceleration is equal to v squared over r, but it's also going to be equal to, and we're going to kind of look at this here, v squared, so 2 pi r over t squared, and that's all over r, okay, like so. If we simplify this, we see that we can kind of say, okay, well, 2 squared is 4, and pi squared is actually, let's undo that, pi squared is really just going to end up being pi squared, and r is going to be r squared. Okay, but what ends up happening is the r down here cancels with one of these r's, and so what we actually see is that only one r is left in the numerator. Okay, and then it'll be all over t squared. And this is yet another equation for centripetal acceleration. It looks slightly more complicated than the v squared over r. It's got more terms, more numbers. However, the big advantage is that you don't have to use two equations, you have just one that models what you need. So in this particular situation, you wouldn't necessarily have to calculate velocity first if you knew the radius and the period or the time it takes to complete one revolution. You can just plug it in and find the acceleration. So this might actually become quite useful depending upon the situation. Lastly, we have centripetal force, and that's kind of over here. Centripetal force is really kind of an easy idea. It's basically Newton's second law, except now instead of using basic acceleration, we're using centripetal acceleration. This is also a center-seeking force, so it has the c here, and the word centripetal goes out in front of the term force. So you have the mass, and it could be times v squared over r. Or it could also be just by adding the mass to the front of this term here, you could turn it into a centripetal force problem. So some really good things here as far as equations and kind of where they come about. And this can be applied not just to a car in a roundabout, but any vehicle, object, item that's traveling in a circle. Okay, so that's kind of it for the review. One of the new ideas today, which I kind of find interesting, is this idea of RPMs. You may be very familiar with RPMs. If you get in your car or your vehicle, or your parents' vehicle, or your grandparents' vehicle, or your clown car, or whatever you decide to drive, okay, the vehicle most likely will have an RPM, or revolutions per minute gauge. It's kind of a cool item, and it tells you how fast your engine is spinning. Now, there are optimal RPMs that your engine should be running at. Some vehicles can run at higher RPMs, some should run at lower RPMs. It used to be that when they had a lot more more mechanical vehicles, less electronics, less computers, that the RPM gauge was very useful for those that drove a stick because it could tell you when you could shift your vehicle. So like I had an old Volkswagen Golf, this thing was a little special, but it was a good vehicle, and my dad and I built it. And so what we do is we knew when to shift. When the vehicle was approaching about 2,000 RPM, we would then shift into the next gear. That way we weren't running the vehicle too long in one gear that was not meant to handle that kind of RPMs. So it is a useful idea, and what we're going to look at today is how does RPMs relate to circular motion. Okay, so imagine for a moment you have two cars traveling in two very different size roundabouts. Okay, so we're going to kind of zoom out here a little bit. You have two cars traveling in two very different size roundabouts, and let's just say that they're both traveling at 10 RPMs. Okay? Now, what this means is that each vehicle is completing 10 rotations, full 360-degree rotations every minute. Okay, so that is a great way of describing their motion. The question on the table is, are they traveling at the same speed? They are both completing a revolution in 10 revolutions every minute. So it would seem that they were kind of, in some way, traveling at the same speed, but are they really? So to look at this, what we're going to do is we're going to say, okay, we know that tangential velocity, okay, or basically how fast the cars are traveling, is equal to 2 pi r over t, or how long it takes them to complete one revolution. So in order to kind of use this, we need to utilize the radius. So for our purposes, I'm going to say that the radius of this one is 1.0 meters. And the radius of this circle down here is 0.5 meters. Okay, so they don't have to be exact. You know, you have 1 meter and a half a meter. This one just needs to be larger, and making it double or 1 seems like a very simple or reasonable choice. So we know what the radii are, but we don't necessarily know this capital T, or in what we looked at on Monday, lowercase t. We don't know how long it takes each car to complete one revolution. So we can figure that out. We know that it completes 10, they each complete 10 revolutions for every 1 minute. Okay? Well, that means, and if we're kind of trying to look at this time in seconds, that they must go around, okay, in a certain amount of time, 10 times, in order to achieve 60 seconds. So what we can kind of think about this is, let's say we have 60 seconds, which is really 1 minute, and we know that in that 60 seconds, that car is going to go around 10 times. Well, if you take 60 seconds and you divide it by 10 rotations, you come out to 6 seconds per rotation. So each object has a velocity. All right, so I'm drawing the velocity vectors here. Each object has a velocity, or each car has a velocity, and that velocity is saying that the cars are going around the path, they're going 2 pi r every 6 seconds. Okay, so now we can figure them out. So up here we'll say, okay, this tangential velocity is going to be 2 pi times 1.0 meters. And we're going to divide that by 6 seconds. And down here, we're going to use the same equation, except that this time 2 pi is going to be times half a meter, but also over 6 seconds, because they both have the same RPMs. And what we're going to see happen here is that this is actually going to become 1/3 pi meters per second. Okay? Whereas down here, 1/2 of 2 is 1. 1 over 6 equals 1/6 pi meters per second. And now what we see happening here is that, those are not the same. The larger circle actually has a faster tangential velocity. 1/3 is larger than 1/6. And pi is the same, so we can kind of, if we're doing a point of comparison, pi doesn't really play in here. So what we're saying is that, this car traveling in the larger roundabout is traveling twice as fast as the car in the smaller roundabout. Even though they complete the same number of revolutions per minute, it's the same number of RPMs, the larger roundabout vehicle is actually traveling faster in tangential velocity terms than the vehicle that is in the smaller roundabout. So here's kind of this idea. This idea of RPMs is actually called, I'm going to just kind of scratch this out. It's called rotational velocity. In rotational velocity, the key here is that it's not dependent upon radius. Both of these circles have different radii, but they had the same rotational, okay, the same rotational velocity, meaning that they were both moving at 10 RPMs. The tangential velocity, so this equation here, also tells us another way of describing how fast the car is going. But this is radius dependent, and the different size of radius will make a difference in how fast the car is traveling. So you have really two velocities in circular motion. A rotational velocity, telling us how fast a car will complete a revolution, and then this tangential velocity, which really tells us how fast the car is traveling along its path. And so these are two very important distinctions to make. Okay. All right, let's move on to the next one. Let's actually look at an example, okay? And then what we're going to do is I'm going to go ahead and have you guys do a couple of example problems on your own. So I'm going to work through this example, and then you'll have a chance at the end of the hour here to try a couple of problems on your own, and then maybe finish up any homework. Just before we kind of move on here, one last plug-in, so to speak, or shout out, is that you have a homework quiz tomorrow, which is Friday. We're going to take about half the period. I'm not going to be collecting the homework packets, but make sure that you are engaged. Make sure that you are, you have your homework done. And so just make sure that you are really actively engaged in looking at the material and prepping for this homework quiz, because it'll be one of your last grades for the semester. And for those of you especially that are on the edge of that 95% break, or you're on the edge of going from a B to an A or a C to a B or whatever, you really want to do well in this quiz, because it's the last homework quiz you will have for this 2013 school year in physics. So, all right, let's take a look at this. You have two gears of different sizes. One has a radius of 0.50 centimeters and the other has a radius of 1.0 centimeters. They are both spinning at 20 RPMs. What is the tangential speed / velocity of each gear? Okay, so the question here is, given a rotational velocity, can we find the tangential velocity of the different gears? Rotational velocity is not dependent upon radius. Therefore, they both can spin with the same rotational velocity. However, they are both dependent. The tangential velocity for both of them is dependent upon radius, and we see the radii are different. So we can automatically assume that the tangential velocities will be different. And from our previous example, we know that the one with the larger radius will have the faster tangential velocity. Okay, so in looking at this, we're going to want to go ahead and definitely, okay, draw a diagram. So I'm going to draw one circle, okay, and I'm going to draw a larger circle. And I'm going to say that this one has a radius of 0.50 centimeters. Now, it's important to remember that in these kinds of problems, we have to use meters, kilograms, seconds. So what we're going to have to do here is we're going to have to convert this to meters, and this happens to be 0.005 meters. Okay, small radius, but I mean on some scales very large if you're looking at microscopic objects. The radius for this large circle, being 1 centimeter, is actually going to be 0.01 meters. Okay, so we now know what the radii are, and in order to use the tangential velocity equation, we need to not only know the radius for the top part of the fraction, but we need to know the time it takes for them to complete one revolution. That information is kind of embedded in this 20 RPMs right here. So the question is, how long does it take to complete one revolution if both wheels are spinning for 20 revolutions every minute? And the idea here is, okay, that, well, you have 20 revolutions per minute, and there are 60 seconds in a minute. So if you take 60 seconds, and you divide it by 20 revolutions into that 60 seconds, what you end up with is a period or a time of 3 seconds per rotation. So now I have the radius, I have the time, I can find v sub t for both of these circles. V sub t for the first one is going to be 2 pi times 0.005 meters over 3 seconds. At this point in time, because the math is a little bit more, you should take out your handy dandy calculating devices, whether it be a phone or whatever, okay? Let's see here. Okay, so I have my handy dandy calculating device out. I'm going to bring up my calculator, and I'm going to go ahead and punch in these values. Now, for our purposes, if you don't have a pi key or you have a simple scientific calculator that you're not sure where the pi key is, you can use 3.14. It's a good approximation, and for our purposes, it's just fine. So, because I'm using my cell phone, okay, and I can turn it sideways and I can look, but there's a pi key, but it took me a little bit longer to find it. Sometimes it's just easier to type in 3.14. So I have 2 times 3.14 times 0.005 divided by 3. And, okay, I ended up with a number. I'm going to double check it. You should be doing this right now. So if you don't have your calculator out and you're not practicing this with me, then you should be. Okay, so just make sure you have your calculators out. All right, so 2. I'll go out of order this time. 2 divided by 3 times 3.14 times 0.005. All right, I got the same number. So it must be fairly reliable. Okay, and that number is 0.01. 46667. Okay, so this is what I'm looking for, and it's going to be in meters per second. Okay, so that's approximately how fast the smaller one is traveling. Now for the larger one, you could do 2 things. You could multiply the smaller one by 2 because it has a radius that is half that, or you can just multiply it all out. Okay, this one's going to be very similar except a different radius. So 2 divided by 3 times 3.14, and it's going to be times 0.01, and voila, you get 0.02, 0.093333. So what we have going on here is that the larger circle has a velocity of this. So we see this relationship that radius is kind of proportional to velocity. If the radius is doubled, tangential velocity is doubled. If radius is halved, tangential velocity is halved. However, the rotational velocity is the same because it is not radius dependent. All right, we're 28 minutes into this, which means that you probably only have maybe 20 minutes left of class. So here's what I want you to do. Okay, moving on to the next page, there is a problem, okay, that deals with a roundabout that has a radius of 100 feet and an initial velocity of 15 miles per hour. What I want you to do is I want you to find the centripetal acceleration and the angular velocity of the car. Now, a couple things to keep in mind here. First of all, you're going to have to definitely do some converting. Okay, this is good practice, so make sure you're doing that. You can use your equations. Make sure that you're being very careful in your numbers, your rounding, and your conversions. I would highly suggest that you work on it maybe in pairs and then check or collaborate as a group to find the answer. Lastly, looking at this last problem here, a 70-kilogram individual is sitting on a merry-go-round that has a radius of 5 feet. It takes the person 3 seconds to make a full rotation. What is the centripetal force holding the person in motion on the merry-go-round? What is the rotational velocity of the merry-go-round in RPMs? I also want you to answer this question. Notice again that there's this value of feet. You're going to have to make another conversion. Okay, you should finish both of these questions in class. All right, and you should be able to go home with no homework tonight. So thank you for watching this video. Lastly, a couple of those reminders, get those reading quizzes done, practice for your homework quiz, check out the homework question forum online, and if you have any questions, you can stop by after school, and I should be there. All right, thank you for watching, and I hope you have a wonderful afternoon.